In this video, we're going to talk about Newton's second law of motion. We're going to start by thinking about a smart car and a dump truck that are sitting still in neutral on a horizontal road. And so you're supposed to get them to do three different things here. And so let's just take a look at our dump truck and smart car down at the bottom. Alright, so if we were trying to speed them up, which one would be easier to speed up? Definitely the smart car. Now, imagine that both of them were moving at 5 miles per hour and we were trying to get them to come to rest. Which one would be easier? Smart car again. What if they were rolling along and we were trying to get them to change directions? And I'm not talking about from inside with the steering wheel, but from externally. We would push on the side of the car and that would be easier for the smart car. Now, why is that? What is the property? Well, two different words come to mind: inertia or mass. And mass is just a quantitative measure of inertia. And so that's the property that's important. Now, what could you do that would cause those changes above to happen more rapidly? Whether you were slowing down or speeding up or whatever, and whether it was the dump truck or the smart car. There's one thing that you could do that would make all of these things happen more quickly, and that is to use more force. That's right. Use more force. So force and mass are important in terms of causing those three things to happen. And we know that all three of these things are acceleration. All right, force causes acceleration to happen, and the more mass something has, the lower that rate of acceleration is. Now, we can put these two things together into equation form. And so we can say that F net equals mass times acceleration. We can also divide both sides by the mass, and so we can also say acceleration equals net force divided by mass. And this particular form right here is really useful if you're answering any conceptual questions. All right, let's check our knowledge. A net force is required to keep an object in motion. Well, let's see. Think about that equation we had on the last slide. If the net force is 0, then that's going to lead to an acceleration of 0. But does that mean we need to have a net force to keep the object in motion? No, we only need a net force to change the motion. Okay, we only need a net force to change the motion. Just like the Voyager 1 and Voyager 2 spacecraft, they're cruising along at 30-some thousand miles per hour, and there's no need to apply a force to keep them going. They're going to just keep on going because the net force on them is 0, and so they'll just keep going in the same direction at the same speed, as long as the net force on them is 0. All right, a tractor trailer has greater acceleration capability than a motorcycle because of the larger net force that's acting on the tractor trailer. That's also false. So it is true that there's a larger force on the tractor trailer. The tractor trailer has a much bigger engine, and there is a greater force pushing the tractor trailer forward. However, remember that acceleration is equal to net force over mass. And so when we look at this, if we were looking at, say, for the tractor trailer, and I'm just going to make up some numbers that are not the actual numbers, but just so you can see, let's say the tractor trailer had 100 newtons of force and 50 kilograms of mass, its acceleration would be 2 meters per second. Whereas the motorcycle, it has less force. Let's say it only has 50 newtons of force, but its mass is also less, but its mass isn't half as much. Maybe its mass is only let's say 5 kilograms, and so its acceleration would be 10 meters per second squared. So it has a much greater acceleration. Okay, so none of these numbers that I put in here, these two numbers or these two, those are not the actual numbers for the mass or force of those two objects. I just wanted to show you how it is important. The ratio of those two numbers is what's important. You cannot just compare the net force, as was done in this problem here. They were trying to convince you that the acceleration would be greater just based on part of this equation. You have to also consider the mass part. All right, the acceleration of a rock is equal to 0 at the peak. Well, let's think about it. It even tells you right here what's acting on the rock at the peak. So if we were to draw a free body diagram, well, we haven't gotten to those yet, but if we were to draw a free body diagram for the ball, or the rock rather, at its peak, the only force acting is the force of gravity. And if that's the only force acting, then the net force can't be 0. Okay? And if the net force is not 0, then the acceleration can't be 0. So that's also false. We also know that the rock is accelerating. A billionth of a second before the peak, the rock was going upward, and a billionth of a second after the peak, the rock is going downward, so its velocity is changing. So it is accelerating at the peak. I hope you have a little bit better understanding of the second law now.